Good afternoon to everyone. Welcome to the project engineering session. We have three rooms running in parallel, all with very interesting presentations, and you are free to move between rooms. At the end of each presentation, there will be a question and answer session. You can make questions during the presentation in the Q&A chat that you can find in the right side of your screen with a question mark icon. As a chairperson of this session, we will have Igor, Galp's project engineer for 3 years, with experience in Brazilian post and pre-salt fields and Texas onshore. Igor holds a bachelor and master degrees in petroleum engineering. Please welcome Igor, and the floor is yours.
Thank you, Natalia, and thank you everyone for connecting. So here with me, we have our first guest, that is Ms. Filipa Castro. So Filipa holds a master's degree in biomedical engineering at Faculty of Engineering at the University of Porto. During her studies, she worked as an intern and in Tech, where she developed an eye tracker-based system for obtaining gas maps for radiologists. She was also an intern researcher in Sheffield, UK, at the Centre of Computational Imaging and Solution Technologies for Biomedicine, working on computer fluid dynamics for predicting the rupture of aneurysms. As her interest in computer vision and artificial intelligence started to grow, she decided to do her master thesis in Delft University of Technology, where she built a dataset and an action recognition system for sports. She is currently a computer vision and machine learning researcher at Abyssal, working on image and video recognition with an ambitious goal of automating subsea operations. Let's give a warm welcome for Ms. Filipa Castro. Thank you, and the floor is yours.
Thank you. I will share my screen. Please confirm that you can see it. Yeah.
Yes, we can see it.
Okay. Thank you. So, hello everyone. My name is Filipa Castro, and I'm an artificial intelligence researcher at Abyssal. Abyssal is a software company that provides a wide range of software solutions for the subsea industry, in particular those related with visualization, simulation, and also remote operations. And we deal with technologies such as augmented reality, cloud, and AI on a daily basis. And today I'm happy that I have the opportunity to share with you some of the research we have been doing on how to automatically detect some subsea entities or even anomalies in inspection videos. So, if you work for the subsea sector, you may already know that subsea inspection or maintenance operations play a major role on this industry. So typically, these operations need to be regularly performed, and they are often recorded using video. And what typically happens is that after these operations, inspection experts may spend hours reviewing video from ROVs and to check the conditions of the field and to spot potential anomalies. Well, our main motivation and the goal of our research work here is exactly to accelerate the analysis of inspection videos by experts and to use artificial intelligence to solve this problem. So instead of spending and wasting hours looking at irrelevant parts of video, we want experts to only focus on parts of video where there is actually an anomaly or a problem. And to do so, we rely on weakly supervised deep learning. This name might seem a bit complex, but I will explain it in simple terms next. And what this model is able to do is to automatically detect the video intervals, like you see here, where the subsea entity or this anomaly is present. And it can also highlight the region in the video where this anomaly is. So besides being automatic and highly accurate, this model can be deployed after the operation, but also during the operation in real time. And this makes it possible for us to build automatic reports after the operation or on the fly. And now I would like to explain, like I said before, how this weakly supervised deep learning model actually works. And for this, I would like to give a practical example where we aim to automatically tell if in a given video frame there is marine growth or not. So what we need at first is input data. And by input data, I mean that we need a lot of videos and a lot of frames. And it's important that among these frames, you have some examples where there is marine growth attached to the structure, for instance here, and some examples where there isn't any kind of marine growth. This is important so that our model can learn these two concepts. So then we feed our model with this data, and we expect our model to predict if there is marine growth or not for each of these images. So basically, what our model will tell, it will assign a positive label if there is marine growth, if it thinks that there is marine growth, and here it thinks there is marine growth on both of them. But if not, it would return a negative label. And on the first iterations of this process, it is quite normal that a deep learning model guesses randomly. So it's very often that is wrong. For instance, here we know that there is no marine growth. However, our model predicts that there is. So he is wrong. And this is normal because at first the deep learning model, which is a mathematical model, hasn't learned anything yet. So it's like a kid. If you haven't told them how to distinguish between marine growth or not, they won't know anything at first. So then how do we teach this model to perform correctly? We need ground truth data. And by ground truth, I mean that besides having the frames, we also need to know which is the correct label for each frame. So here the correct label is a positive label, and here it's a negative label. And by having this information, we can compare with the output of the model, like you see here, and then we can give some feedback to this model and tell him, okay, here you got it wrong. There is no biofouling. And if we give this feedback, we will update the model parameters, and next time we expect that its predictions are better. So that's actually how a deep learning model trains, and it trains for several iterations until that we are okay with the desired performance. So now imagine that instead of wanting to know if there is marine growth or not, you also want to detect where this marine growth is. So the logic and the functioning of the system is the same. The only difference is that the model also predicts where the marine growth is with these kind of bounding boxes. And to train this model, our ground truth also needs to have bounding box annotations. For instance, here you see that the correct annotation is a bit bigger than here. So we need to provide this feedback to the deep learning model so that it learns for the next iteration. And the problem here is to obtain this ground truth for training these models. It is very time consuming because you would need to have someone spending entire days just drawing these boxes around these frames. And to avoid this and to make this process much more efficient, what our research does is that it tries to still obtain this kind of information about where the marine growth is, but while relying just on this kind of information. So we just want to provide these negative or positive labels, but at the same time we want to achieve this kind of output from our model. And next I will explain how we do it. So to do it, we use what we call weakly supervised learning. Instead of feeding the model with entire images, what we do is we split these images into different blocks or different regions, as you prefer, and we feed them to the model. So here we expect to obtain a prediction from our model for each one of these regions. So if the model thinks there is marine growth here, it will assign a positive label. If not, it will assign a negative label. Instead of having one label for the entire image, we have per region labels. But then we have the problem that in terms of ground truth, for training, we just have one label and we don't have per region labels. So how can we compare this kind of information with this kind of output? So what we do is we apply a max pooling function, and this simply means that if there is at least one positive prediction in one of the regions, we will consider it to be positive. If all of them were negative, which doesn't happen here, we would consider it to be negative. And then we can finally compare it directly and actually train the model. But now you might be asking how we can obtain the location of the marine growth. So, because this just tells me that there is marine growth, but I want to actually know where it is. So we will rely on this intermediate information. So we will take a closer look on this step to understand how we can obtain this. So considering that, like I said, we can split our image into a lot of different regions, tiny regions, and considering that we will have the model predictions for each one of these regions, what I do is that we apply a Gaussian and a color mapping. So by Gaussian, I just mean that instead of taking into account just a prediction for each region, I will also take into account its neighbors. And then I will apply a color mapping just to give the intuition that high intensity, like red, means that the model is highly confident in this region that there is marine growth. And as we get closer to the background, this intensity is reduced. So what we obtain is something like this. This is an attention map, and what we see is that the red color represents the region of the central region of the marine growth, and it kind of delineates in a great way the region where the marine growth is attached to the structure. So in terms of objective results, the first thing we did was to evaluate the classification results for 3 different tasks. So the tasks were to find underwater structures in video, to find marine growth, and to find ROV in video. And our baseline is represented in blue, and we can see that, for instance, for the underwater structure, there we have 98% accuracy. This means that if you give us terabytes of video data from ROVs, we can tell with high reliability where there are underwater structures within your video. So you may have hundreds of hours, and within seconds or minutes, we will tell you exactly where you should look at the video to find underwater structures, to find anomalies such as marine growth, biofouling, or even to find ROV. And the post-processing here, represented in red, it's a simple processing that we apply basically to remove outliers and to take into account the video sequence that we have. So imagine that we have 1 minute of video, we extract 1 frame per second, we have 60 frames, and all the model predictions say that there is marine growth on these frames except for 1 frame. So our post-processing assumes that this frame is an outlier, and we should consider that also in this frame there is marine growth. So this is a simple approach. but it can actually improve results a lot. For instance, for marine growth, we can see that it improves by more than 6% of accuracy. In terms of qualitative results, here are some of the attention maps we obtained for the task of detecting subsea structures. And I must say that you are looking at videos that were not seen by the model. So the model trained with some fields and some structures, and then it was tested with completely different ones. And we can see that this approach has good results for different structures. You see here a pipeline, we have plates, we have manifolds. Here also there is a bullnose. And it actually is able to accurately delineate the structure of interest. So we have different video resolutions, different ROVs, and different fields, but it's working fine for all of them. Here are some of the results obtained for the marine growth. Again, you can see, for instance, here we can say that the output of an attention map may even be better than having a bounding box, because if you had a bounding box, it would simply draw something like this, and it would miss these details of the borders of the marine growth. And finally, some of the results regarding the test we did to detect ROVs. Here again, we have different ROVs, different manipulators, different operations, different video resolutions, and different backgrounds, as you see. But we are able to detect the region of the ROV. And actually, what was quite surprising also for us is that when there are two instances of the ROV in the same frame, we can actually detect both of them in an accurate way, which is good. And I would like also to say that detecting ROV is extremely relevant if you want to go one step forward and go towards autonomous operations, because imagine that you want your ROV to autonomously rotate a valve, then you would need to know exactly where the ROV manipulator is. So you need to understand what you are seeing in video to then manipulate and train your ROV to perform it autonomously. So these are some additional results. Basically what we did here was to use our attention maps to obtain what we call a segmentation map. So we just apply a threshold, and then we have in white the pixels that belong to the structure, and in black the pixels that don't. And for instance, here you see that there is a ruler, so a tool that belongs to the ROV, and it's here like taking some measurements to the marine growth. And our model is able to correctly say that, okay, these pixels do not belong to the structure. And this is really important because one of our other research focus is on 3D reconstruction from video. So we want to reconstruct the environment that is surrounding the ROV just with video. And for this kind of approaches, it's really important that you discard the pixels where there are moving objects like the ROV arm or this kind of tools. So we are using this kind of output from this method, this automatic method, to then feed our models for 3D reconstruction, because then you can tell to the 3D reconstruction algorithm that it just needs to look at these pixels, because these are the relevant pixels containing the structure, and that's the structure that you want to reconstruct. So to sum up, I would like also to talk about, to give an overview in terms of the efficiency of our method. So in terms of annotation, like you saw, typically you would need to draw these bounding boxes, but in our approach, you just need to tell that there is marine growth. So you just need to do one click instead of drawing 4 or more bounding boxes, and this is actually more than 100 times faster in terms of annotation. In terms of training, because we use a weakly supervised model, this is lighter and also twice as fast. And in terms of results, as you can see, they are pretty similar. So we can say that we have the same accuracy, but we can run in real time because the model is lighter. And now you might be asking how you can use these kind of methods in your case study or your use cases. And so we provide, we have a solution which is called the Abyssal Cloud Platform, where you can log in anywhere in the world, and then you can access the video library where you can upload all your videos, and we will run our AI models on top of that, and you can access the results within minutes. We are using this technique also to detect text on overlay video, and this means that you can upload terabytes of video, and then we can extract in minutes all the information that is placed in the overlay, and then we can use this information to get some insights and play with some analytics. So basically, any kind of use case that we have to solve with AI, the approach would be to log in our cloud, to upload your videos. We would run the appropriate model on the cloud, and then you can access the results in the video library or even in a 3D environment. It will depend. And you can also download a report or deploy the solution in real time with our offshore product. So I'd like to thank Galp again for the invitation to be here today. Thank you for your presence and for your attention. And I'm now open to your questions. If there's no time for everyone, please send me an email and visit our website. Thank you.
Thank you. Thank you so much, Filipa. Just remember for the attendees that you have an icon in the top right of your screen that you can make questions. So I have a couple of questions here for you. So the first one is that as you mentioned, it's a machine learn. So as you put more data, the machine learn more and learn faster and better. But you I think in slide 8, you told us about 95% of accuracy. How much data or the amount of data is necessary to achieve this accuracy? You said some terabytes, but sometimes we don't have this amount of data available. So to achieve this accuracy, how much of data do you need?
Yeah, I mentioned terabytes just to tell you, to assure you that in our cloud you can send as many data as you have. But actually to run these results, I can tell you that for the attention maps, for instance, we use around 200 minutes of video, so it's not so much. Because one of the things is, of course, everyone tells that you need a lot of data, and that's very important, but it's also important that you have a wide diversity of data. For instance, for us, it was 200 minutes of video, but these were videos from 8 different missions. Inspection missions or maintenance missions. So if we had just one mission from one client and one field, it wouldn't perform so well on a new test set. But if you spend some time curating your data, and if you have the right data, you don't need so many images or videos. We have another example where we did automatic pipeline inspection to segment different anomalies on the pipeline, and we used around 600 images.
Okay. My next question is about the model. So you say sometimes that it is capable to predict submarine growth. But my question is, you have different types of animals and lives in the sea. So how can you predict this kind of growth when you have different environments, different water qualities, different marine lives? How the tool works to predict this?
Okay, so if you want to just predict if there is marine growth or not, even though there are different types of marine fouling, for instance, there is soft marine fouling and hard marine fouling, the texture and even though there are different organisms, the texture and the color will always be the same or more or less the same. So as we trained in the wide diversity of depths and different fields in different parts of the world, we just have we already have samples from everywhere, so we already know how it looks like everywhere, and that's why we can tell that it would work fine for any part of the world. But then if you want to clearly tell if this part is soft marine fouling or hard marine fouling, there we would need some expert annotations. So we would need someone to tell us what is marine growth soft and hard, and we would need to tell that to the model and to teach the model. So here, like I explained, how the logic works about teaching your model. Here we are just teaching him that there is marine growth. If we wanted to tell if it is soft or hard marine growth, we would need to have different labels and have different examples for soft and different examples for hard. And after a few iterations, you would hopefully learn it.
So, and my last question is about the savings that you said. So, since I understood, the biggest savings is related with man-hour that analyze the data, so it's much faster than a real person and a learning person. But my question is, do you expect with these models and the capability of predict almost the future to have less ROVs interventions, like you can predict more or less the future of growth and have less ROVs travels?
Yeah. So yeah, I mentioned mainly the fact that if we apply these models after the operation, we will reduce the time that experts spend looking at the video. But actually, there are some kind of operations. For instance, we had a case study where the goal was to characterize the marine fouling of the operation. And what happens when you try to do this is that during the operation, you need to take some manual measurements during the operation. And it takes a lot of time. You have the ROV there, you have the vessel there, the crew there. And what we did was tell the client, okay, you don't need to take these manual measurements anymore. You just need to pass through the leg or the jacket one time, provide us with a video, and then we will take these measurements and this automatic detection. So instead of spending 1 hour underwater with ROV, they just need to spend 10 minutes now. So this is a highly reduction operation. So you will need less time and less ROVs for sure.
Okay. So thank you so much, Filipa. We are almost out of time. So if anybody has more questions, they will address to us and can send some emails. But thank you so much for being here and for your presentation.
Thank you, Igor.
Bye.
Good afternoon.
Bye.
Great event. Bye.
Thank you. So I think we have already here our next guest. This is Sir Peter Adam and Kirk Stalis. Hello. Can you hear me?
Good afternoon.
Good afternoon. Yes. Okay, perfect. So I can hear you and I can see you.
It's a good start.
Yes, for sure. So I'm just waiting.
Are you able to see my screen?
Yeah, for sure. I'll just present my next guest here, as I already spoke, Sir Kirk Stalis and Peter Adam. So Sir Kirk Stalis has more than 20 years experience in rotating equipment industry in various roles of engineering, project management, business development, commercial, and proposal management. He is currently the proposal director for gas turbine at Siemens Oil Gas. He holds a Master of Science degree in Mechanical Engineering and an MBA in Management, has a patent in rapid prototyping. Sir Peter Adam has more than 35 years of experience. His background is in electrical engineering for the University of Applied Science in Dieburg and Technical University of Darmstadt in Germany. So he has a really vast bio. So it's a pleasure to have you here. And I will just summarize some in few words because you have a lot of experience, and thank you so much for coming here. So passing through the different areas inside Siemens, starting as an electrical engineer to sales director, and then vice president of joint venture, vice president of oil and gas upstream, head and account manager of project development, and vice president of market development board, and head of strategy and chief of technology officer. And currently, Sir Peter is the head of sustainable and hydrogen business development. So once again, thank you so much, Sir Kirk Stalis, Mr. Peter Adam, the floor is yours.
Thank you. First of all, I want to thank you for the invite to share this presentation. So we've prepared about a dozen slides and then intend to basically leave ample time for questions at the end. Okay, so Peter and I are going to discuss the decarbonization of the oil and gas industry, mainly focused on the rotating equipment typically used in production environments and upstream and downstream. So mainly around the compression and the gas turbines and the power generation applications for the processes. So today, it's one of the bigger topics out there, obviously, is how do we maintain production while meeting our CO2 commitments. So it's a massive topic and a massive challenge that we all have in front of us. And what we are going to discuss is things and techniques and technologies that we can do today to achieve CO2 reductions, and then also discuss up and coming technologies and fuels for the future. So just speaking a bit about offshore production that we typically see, offshore production is mainly dominated by focus on production, where production is king. So reliability, dependable equipment is key. And many of the offshore projects that we see has very limited regulations. So any initiatives that companies take on is generally on their own accord, on their own corporate sustainability goals, where they choose to implement technology to minimize the CO2 footprint. Some of the ideas that people use today, or some of the technologies they use today, is what's called dry low emissions technology on the gas turbine. It's basically the combustion of the gas turbine is done in a certain manner to minimize the NOx and the CO production out of the machine, and we'll talk a little bit about that. But it has limited use today offshore. So my personal experience is it's less than about 20% of projects that we see where they adopt this DLE technology offshore, even though it's pretty much the standard for onshore. And then there is some applications, or there's many projects out there that would benefit from electrifying the topside process equipment. And I'll talk about that in a couple slides. And then also utilizing combined cycle techniques, which are quite common onshore, but very, very limited offshore. And I'll talk a little bit about that. So focusing on the DLE technology, so in gas turbines, there is the combustors, which is basically where the fuel is burned. So it's taking the methane and basically introducing a spark, and then igniting the fuel, which then produces the hot gas, hot pressurized gas, where you extract the power out of it. So there's many different ways of combusting the fuel. So typically most gas turbines fall into two categories between what's considered a non-DLE combustor and a DLE combustor. DLE being a dry low emission combustor, which when we look across the different applications in different industries, the DLE combustor is pretty much the standard for onshore applications. So typically in power plants or pipeline stations, or even in downstream refineries, typically we see DLE combustion technology is pretty much the standard. And that's mainly because of the regulations require it. And it also minimizes the environmental impact of the project. However, when we get to offshore applications, the adoption of DLE is actually quite limited. And so this is one opportunity where many projects would benefit from using a DLE combustor for all of the gas turbines on their facility. And this is, different OEMs have different technologies with where some of the DLE combustion can be sensitive, and some OEMs have DLE technology like Siemens does that does not require frequent adjustments or tuning, and it produces very, very low emissions in terms of NOx and CO coming out of it. But if you start just to quantify, what the benefit is, it's about a 20 times reduction in the emissions coming out of the back end of the gas turbine by using DLE versus non-DLE. The exact number will vary on power duty and what size machine and such, but just as a rough frame of a reference, you can lower your footprint, environmental impact by about 20 times. A NOx footprint, for example, if we adopted this as universal offshore. Okay, another concept that I wanted to share with you is the electrification of the topside modules. So traditionally in FPSO, this is an example on the left-hand side of an FPSO that is about 100,000 barrels a day FPSO. Typically, there would be 4 power gen units where 3 are operating and 1 is in standby, and then there would typically be some gas turbine driven compressors or some motor driven compressors or a combination of both for the overall topsides production. And companies tend to try to mix and match or usually match the gas turbines that are used and on the vessel for maintenance reasons and operator familiarity. But the reality of when that is done, you have a gas turbine that is running at very low loads and generally not very efficient. And so one of the concepts that the industry would benefit greatly from is basically converting the whole production facility to being electrified. So on the right-hand side is a comparison of what it would look like. So basically what gets done is you end up using larger gas turbines for your power generation on your platform or on your FPSO, and then the rest of the facility is basically running off of motors, and the full facility is electrified. And so the benefits of doing that is, well, first and foremost, there's an efficiency benefit to basically running gas turbines at close to their 100% load condition. So you end up with an efficiency improvement, but you also get a CapEx benefit to where motors are generally much less expensive than a gas turbine, and your OpEx is also much less expensive because generally motors require less maintenance than a gas turbine. But if the industry adopted, as electrification as a standard, effectively their efficiency of the overall system goes up, and more importantly, the CO2 footprint of the vessel would be reduced from anywhere from 5 to 15%. So just by using today's technologies that have been around for many, many years and are currently in service, many different applications, just reconfiguring the topsides modules and how we use the power generation and the compression modules would benefit from basically it would yield an improvement in the efficiency and also in the CO2 footprint related to that production. Another solution that's available today is combined cycle, which generally does not get used very much offshore. But if we looked at a similar duty to what we just looked at for a typical 100,000 barrel a day production facility, on the left-hand side is the kind of the electrification solution I just shared with you. And on the right-hand side is what it would look like if it was a combined cycle solution. So basically, converting one of the operating gas turbines, combining it with a boiler and with a steam turbine applied to it, would yield even greater efficiency. So you go from basically an open cycle efficiency of call it roughly 35% on the gas turbines up to over 50% and close to 60% from an overall efficiency, which at the end of the day yields about a 25% reduction in the CO2 footprint. And just to try to quantify how much value is there and how much benefit it has to the environment. So if you just compared that savings in CO2 of over 100 tons a year, that's basically a small city or a small town of what they produce. So it's just one example of what can be done today to basically decarbonize some of the offshore production facilities. So the picture up here on the right is a solution that's been developed that we refer to as the ultralight combined cycle solution, where it's quite compact and it's really been optimized for offshore facilities. So it doesn't come with all the drawbacks that traditionally an industrial combined cycle solution would have. And then I'm going to hand it over to Peter to talk about some of the technologies for the future.
Okay, thank you, Kirk. I want to now switch over to downstream and use a couple of examples. When we consider olefin is one of the most widely produced chemicals, and a 1.5 million ton plant, what is a world-class plant today? Oh, you switch forward, go back.
Oh, sorry.
Okay. Needs a furnace power of 900 megawatt, 400 megawatt for process heat, and 100 megawatt steam turbine power requiring 500 megawatt heat in the furnace. And the furnace is basically burning residuals or feedstock. And a 1.5 million plant then in average emits 2.4 million ton of CO2, and in Europe with a looming CO2 tax in a couple of years has to pay 120 million euro CO2 tax. How this can be reduced? When we would integrate 3 60 megawatt combined heat and power gas turbines parallel to a much smaller furnace, we could use the electricity generated in the turbines, the 180 megawatt, to convert all the steam turbines to electric motors. Electric motors have a much higher efficiency than steam turbines. That means the overall energy demand goes very substantially down. And in addition, we would use the exhaust heat of the gas turbine to preheat the feedstock, what then would lead that the remaining heat that need to be generated by burning something in a furnace is reduced to 130 megawatt. And by doing so, we would reduce the emissions of the overall plant by 50%, and what gives then a saving for the plant of 60 million per annum. And I believe in particular in Europe, later in other countries, this will be a concept where we can help the industry to reduce their CO2 footprint and the associated costs very substantially. Could you switch forward? Kirk? Oh, fine. Now switching to hydrogen. Today, hydrogen is produced roughly 74 million ton per annum, and 95 or 98% is produced from gas, coal, or oil using steam reforming or ATR processes. And by doing so, also generating a lot of CO2. And of course, a steam reformer producing hydrogen is basically the first process step in many processes, mainly ammonia, refining, methanol, and so on. And in order to achieve the projected CO2 reductions, many countries have committed themselves. The hydrogen production need to increase roughly to 500 million ton by 2050, what would mean plenty of those plants need to be built, and of course emissions would go up. Switch forward, please. Kirk? Oh, fine. Let's switch a little bit to hydrogen itself as a media, a gas to be transported. There are a lot of discussions ongoing whether hydrogen will be blended in existing natural gas pipelines or not. But in our discussion with pipeline operator, it seems to be that the operator more prefer to build or use a dedicated hydrogen pipeline grid parallel to the existing natural gas grid. And they have already identified, and you see here the map of Europe, the existing natural gas pipelines to be converted to pure hydrogen pipelines, because that had certain benefits. And there is a myth communicated that when you use the existing pipeline and you transport hydrogen, the pipeline only has 1/3 of the energy transportation capacity due to the lower energy content of the same amount of hydrogen compared to natural gas. But the flow pattern of hydrogen molecules in pipes is very much different from methane, that you can pump, keeping the design pressure 3 times the quantity at the same time to the pipe, and therefore in a converting existing pipe would mean you can transport more than 90% of the energy compared to methane in those pipes. And this is really going on. Of course, doing so means you need to increase the compression power 3 times. And I repeat myself, the European pipeline operator have identified the pipes in the map, and dialogue has already been started to the respective governments and European community on regulations to convert those pipelines into a hydrogen transportation grid in Europe. Next page, please. Okay, then the hydrogen, everyone talks about it, how it's used. It comes from various sources. Today, everything is gray with a lot of CO2 emissions. In future, we will have blue hydrogen, where the CO2 is captured from steam reforming and put into oil and gas reservoir for storage. There is, of course, the green hydrogen, where the hydrogen is generated by electrolysis from renewable power. In particular, in France, probably nuclear power will be used also to make hydrogen by electrolysis. That is then defined red. And of course, although in the midterm future, we probably will see pyrolysis, what is defined as cyan. But when we look at how it's used with all those many projects, I think the biggest short-term usage is to use it in refineries, building in refineries small or medium GTL plants to make synthetic fuels for heavy trucks or airplanes, because that is the only way that is perceived at the moment to decarbonize transportation in this area and to fulfill the RED II regulations. And of course, the next important usage will be in the chemical industry as transportation fuels, provided that fuel cells become competitive. And then, of course, further on in cement, metal, or even in power plants. Next page, please. Okay, in this picture I have illustrated basically a little bit the hydrogen value chain, where it comes from and where it is. And of course, it needs everywhere compressors. And then you may argue hydrogen is something new, but it's absolutely not new, because hydrogen is used in the industry since many decades, and we have supplied hydrogen compressors for over many decades. It was just not so prominent in everyone's mind due to the green hydrogen was not down there. The basic message is the technology to compress hydrogen is available. There will be some challenges to have turbo compressors efficiently pumping hydrogen, huge quantity in pipelines, but although this is technically addressed and will be available in the near future. Next page, please. Okay, here you see roughly a map where you can see the current capabilities of the Siemens gas turbine fleet in burning hydrogen. And so we are currently in progress for a customer in South America to implement a couple of 25 megawatt turbines to run actively on 60% hydrogen in the fuel gas. And therefore, I think there will be upgrades available that all the major turbines can be converted to 100% hydrogen. But the need to have some is limited, in particular for the big units, because there's just not enough hydrogen available on short notice to provide the hydrogen fuel for a large turbine. We go forward, please. Okay, but making hydrogen is at the moment generating a lot of CO2 emissions. Today, 75 million tons of hydrogen is produced, and this leads to 675 MTPA of CO2 emissions. And of course, these emissions need to be taken care of, otherwise the industry will not accept it, and also the regulators not. That is basically the conversion from today gray to in future blue hydrogen, where the CO2 is captured. In a traditional solution, you have a furnace and the water gas shift, where those CO2 is generated and currently mainly released into the atmosphere. Sometimes small quantities are used later in the process, for example, to making methanol or something. I also used an example here for a certain steam reformer producing 150,000 tons of H2 in a year. It would generate 1.35 MTPA of CO2, and by doing so, in future face a CO2 tax invoice of 67 million per annum. Same principle then in olefin, adding a gas turbine in combined heat and power application parallel to the furnace, preheating the steam and the feedstock would provide roughly half of the energy into the furnace, and by doing so, we can reduce the furnace cost emissions, although in a magnitude of 50%, whereas technologies are already available to take care of the CO2 from the water gas shift, and therefore, in the combination of both, the CO2 emissions of the steam reformer can be reduced roughly by 4/5. And again, for the furnace alone, the savings would be 12 million a year for such a relatively small plant. The next page, please. Okay, that's it basically. We are all here for questions.
Thank you so much, Peter, and thank you so much, Kirk. So we have a couple of questions. I will start the first one with Kirk. So regarding I think it's slide 5, regarding top sides, and I will ask questions more related to the offshore world. That's our reality here at Galp. So you mentioned that's a usual solution to replace those gas, the turbines for electric motors. But at least in Brazil, where Galp has some operations, we have a limitation for IBAMA, is the environmental entity that limits us to only 100 megawatts of power generation. So in the next slide, you more or less answered my question regarding combined cycles. But I mean, how can we overpass this limitation and still having electric motors, since we can only have 100 megawatts?
Yeah, so it's a good question. So in Brazil, this offshore regulation that I think you're referring to that limits it for 100 megawatts basically applies to non-DLE solutions. So the Brazilian regulations that I'm familiar with is if you go over 100 megawatts of production or for power generation offshore, then it does fall under the regulation that requires DLE combustion. And so in order to do this electrification solution, you basically have to use a gas turbine that produces emissions and that is compliant to the Brazilian regulations, which is 25 parts per million NOx. So using gas turbines that are available today in this power block, as long as they're DLE, the low emissions technology, it is compliant to the requirements. Where the operators offshore run into trouble in Brazil or the lease FPSOs is they tend not to want to go over 100 megawatts because they're resistant to using DLE offshore because of concern around reliability. And the reality is there's been some DLE machines put offshore that has had reliability issues, 10, 15 years ago, but the technology has come a lot further, and different OEMs have different ways of designing the DLE combustors, and some are much more robust than others. And so just without making it too salesy or too much of a sales pitch per se, but just the very simple answer is this electrification solution can be done offshore Brazil, provided the gas turbines are DLE.
Okay, thank you. Yes, you are completely right. So the regulation is more related to the CO2 emissions than to the power generation itself for the gas turbine. But the second question is, when you change for electrification in terms of loads, because sometimes we have FPSOs with almost topping on loads. So can you elaborate a little bit on this?
Yeah, so this electrification solution, so typically one of the concerns is when there's a process interruption and load sheds or load rejections or step up of loads. But the beauty of this electrification solution is if you're running at 40 megawatts and then you suddenly drop 15 megawatts of load, or you add 10 megawatts, or you add 15 megawatts of load, it's a relatively small percentage of the power of the gas turbine, so it doesn't cause any sort of a frequency disruption on the grid. Where operators have some challenges is when you're running smaller gas turbine power blocks, and then you shed a 20 megawatt power block when your gas turbines are 20 megawatts. You potentially have some over frequency or under frequency issues. But the beauty of the electrification solution is the motor-driven compressions are a relatively small percentage of the total operating power. So they call it the grid inertia or the grid dynamics, don't really care about call it 20, 30% load shed or a load add event.
Okay.
So it's a much more stable grid.
Okay. Thank you, Kirk. So the next question is for Peter. So Peter, your speech was about the hydrogen. So do you think we are much far from having these innovative solutions offshore? So we know that we are in the third generation of FPSOs, going to the fourth one. But how long do you think will it take to have this kind of solutions offshore?
We are already in discussing with FPSO companies, although companies who build FPSOs, that are basically looking at concepts how hydrogen generation facilities can be put offshore. First of all, to be parked maybe in the middle of a wind park, making locally the hydrogen and then pump the hydrogen onshore instead of electrical energy. And also what we see is that when the decarbonization needs of the offshore operations, for example, goes further, of course, when you use hydrogen as a fuel for the gas turbines, you have no emissions anymore. And I think in particular the gas turbines used in offshore in the 35 to 40 megawatt range will be the first available for high-grade hydrogen available. And we are also in discussion with companies who will provide process solutions, how to say it, that you can more or less generate locally on a vessel the hydrogen to be used as a fuel in a gas turbine, and then the emissions are basically zero, and you still have your operations.
Okay. Okay.
So I
we are
think
not
those
so far.
kind of technologies will be available in a couple of years.
Okay. Okay. Good. Really good. So I have a lot of questions regarding the subject, but unfortunately the organization is telling us that we are out of time. So thank you a lot for your presentation. I will address the other questions by email. So thank you, and thank you, Kirk, for the presentation.
So thank you very much for the opportunity to speak to you today.
Thank you. Bye. So I think I have already here Mr. Pedro Panta. Can you hear me?
Hi. Yes, yes.
Hello.
Clearly.
Good. Okay, good. So just to remember the attendees that you can make questions during the speech. You just click in the icon in the corner of your screen in the top right. So you can make questions, and then we will pass for our presenter. So Sir Pedro Panta is a technical consultant at Ouro Negro and is involved in equipment projects for intelligent well completions. He has 18 years of experience in R&D at the oil and gas industry, including 7 years at Ouro Negro. He has 1 patent filed in the several works in the oil and gas area. Pedro is currently leading the project development and laser hydrate dissociation tool in partnership with Galp. Pedro holds a bachelor's degree in mechatronic engineering from the National Engineering University in Lima, Peru, and master's degree in mechanical engineering for COP UFRJ in the area of robotics. So thank you so much, Sir Pedro. The floor is yours, and have a good presentation.
Thank you very much. Good afternoon. As Igor said, my name is Pedro Panta. First of all, I would like to thank Galp for the opportunity to expose one of Ouro Negro solutions. Talking about Ouro Negro, where I am proud of working for 5 years, is a Brazilian company of technological innovation oriented to the development of intelligent solutions for E&P sector of the oil and gas industry. Nowadays, we have a project in progress with Galp, Pedro Galp, as Igor said. It rated this association tool using laser radiation, whose fundamentals we had the opportunity to show in the last edition of the Galp Open Day. This year, I am pleased to show you a system designed by Ouro Negro in the area of well decommissioning. The kitman showed here is intended to be a solution that takes advantage of the technological knowledge to reduce cost and time of an operation that seems to be complex using traditional methods. In order to understand the problem a little better, this work has as its main motivation the monitoring of wells in temporary abandonment required by the resolution of the National Petroleum Agency of Brazil. When I talk about wells in temporary abandonment, I mean wells that are abandoned waiting for permanent abandonment, wells waiting to be assigned to small companies to continue the end of the well's useful life, or even to new wells that are waiting to connect to some production platforms. Currently, there is no equipment that is fully complying by the resolution referred to the ANP Well Integrity Management System, SEGIP. We focus here on the temporary abandonment wells market that awaits permanent abandonment to understand some of the complexity of the problem, assuming that operators want to avoid temporary monitoring, they will have to begin the process of permanently abandoning more than 1,000 unmonitored wells. And they have to do it in a maximum of 3 years, which is the maximum time allowed to maintain a well without monitoring for operators who opt for permanent abandonment. With current resource, they encounter two adversities in Brazil. The first one is economic. Making a quick calculation nowadays, it takes 60 days approximately as the average estimated time to perform the permanent abandonment wells, and the average estimated daily cost of per rig equipped for this kind of operation is an estimated average cost of $500,000, a little less perhaps because of the crisis, giving a total estimated cost of $30 million to abandon a well permanently. So we are talking about more than 1,000 wells to be abandoned permanently. We are talking about billions of dollars of magnitude. The second problem is the number of rigs keep it for this type of operation in the country for the maximum period of 3 years allowed by the resolution to decide to abandon a well permanently if the operator does not decide to monitor the well. We have about 16 rigs, considering that the operation time takes almost 2 months. We are talking about hundreds of months. This is, of course, if the rigs are only available for the permanent abandonment operation. That's not true. We conclude that there is a large liability to be fulfilled by operators where monitoring of wells in temporary abandonment presents itself as a viable solution. Therefore, to mitigate the well abandonment market in Brazil, our purpose is to implement a system that monitors the two well safety barriers and check their integrity as required by the ANP resolution. But it's clear that we do not have a universal technical solution for all the wells that needs to be monitored. For this reason, our proposal is limited to wells with some characteristics that include a considerable number of the wells that need this monitoring. First, our proposal applies to wells with wet Christmas tree that have also installed the vertical connection module, VCM. In addition, there is a great possibility of dealing with all Christmas trees. Our proposal also considers that the sensor of the tree might not be working properly, and that is why our equipment comes with its own embedded sensors. Finally, for the same reason that we are dealing with all trees, our system preserves the operation of wet Christmas tree safety valves as much as possible to check the integrity of the well safety barriers. To better understand the technology we intended to use, I will describe the installation process of the equipment whose external appearance is shown in the figure. I hope that by explaining this process, you will have a better understanding of the application scenario as well as the main components of the invention. After that, I will make a simple application example to understand how the equipment will operate. I will try to be very simple in this last explanation because it is more technical, but it is a necessary explanation for you to get the idea. This drawing depicts a wet Christmas tree with 3 vertical connection modules still installed. A module with access to the annulus of the well, another with the access to the production tubing, and finally a module with access to the control of the Christmas tree safety valves. This situation shows an advantage of our proposal since we can take advantage of the operation that has to be done to disconnect the wet Christmas tree. That is, we took advantage of the tree disconnection operation to install our monitoring system, which makes installation costs cheaper. To begin the process of installing our equipment, first the disconnection process of the vertical connection modules occurs. Afterwards, a modified abandoned cap is installed instead of the traditional abandoned cap used to protect the hubs. Then, on the modified abandoned caps, a control module is installed that will have access to the control valve of the wet Christmas tree, and two register modules that have access to the production tubing and the annulus of the well. The control module is connected to the register modules in order to centralize control and access to the production tubing and the annulus of the well. Finally, a connection is made between the communication module embedded in the ROV and the control module, which will allow the monitoring and checking of the well safety barriers from the surface. Now we have we can have a better understanding of the figure showed earlier. Here, the three modules and the ROV. The drawing showing a representation of what will be a wet Christmas tree. Here, the two register modules that already explained have access to the production tubing and the annulus of the well. These modules comprise one of the main components of the system, which is the safety valve included in them. This valve increases the safety of the operation of our system, since it is intended to be a redundancy of the well safety barrier. Another important component of this register module is the pressure sensor that gives us an idea of the pressure in the chambers of the production tubing and the annular one. As explained earlier, the control module is connected to the register module in the installation process, so that the control module centralizes the operation of the system. This connection is made by hydraulic connection hose, through which it is intended to have access to the chambers, either of the production tubing or of the annulus of well. An electrical cable through which the signal from the pressure sensor is transmitted to the control module, and hydraulic hose to control the safety valve of the register modules. Here we can see the control module, which we can access the chambers, safety valves, and sensor of the wet Christmas tree, as well as we can collect or inject material from the well if necessary. This control module will be the interface through which the ROV will monitor and check the well safety barriers. The ROV that will be responsible for the operation of the system, and that will be that we will have to be equipped with tanks of hydrate inhibitors necessary to prevent the formation of hydrates while carrying out the pressurization and depressurization process. Now I will go back a little bit to the basics to explain how the system intends to check the safety valves of the wet Christmas tree. The methodology of operation of our equipment is based on the pressurization and depressurization of the chambers next to the safety valves to later infer the leak in them. An analysis of the resulting leak will infer if the valve is still within the range allowed for the current operation. I will show briefly a brief example of how this works. Here is a schematic of the inside of a wet Christmas tree to see some concepts and understand how the proposed system works. When I talk about the wet Christmas tree safety valves, I mean, of course, the master and the wing valves 1 and 2, as well as the subsurface safety valve. The secondary well safety barrier is shaped by the wet Christmas tree safety valves, and the surface subsurface safety valve is part of the primary well safety barrier. Let's go to our example where we explain how the Wing 1 checking will work. For that, I will depressurize chamber 1 using the corresponding resistor model and pressurize chamber 2 by means of chemical injections. Once it is done, the system will measure the pressure growth rate in chamber 1 through the corresponding resistor model, thus inferring the leak in Wing 1. If the leak is within the acceptable range, we can infer that the Wing 1 is okay, otherwise Wing 1 will be degraded. There are some challenges for the implementation of the proposed system. The first one is the difficulty of depressurizing the annular well if necessary. This is because the amount of material extracted from the annulus is likely to be large. The second challenge is the lack of standardization in the interfaces of the vertical connection model in wet Christmas tree. This will create the needing of customization of each equipment made. Also, as already mentioned, there is a possibility that we will find a Christmas tree that is very damaged by time. Therefore, even if the operation of the proposed system avoids operating the safety valves of the wet Christmas tree as much as possible, there have been cases where it is inevitable, leaving the risks involved to the operator. For our understanding, there are some clear benefits of the proposed system. The equipment, by complying with the AMP requirement, contributes to the monitoring of wells in temporary abandonment, guaranteeing operation safety and preserving the environment. The proposed system develops technologies for the performance of wet Christmas tree, access to well chambers, and leak measurement in safety valves. Finally, but no less important, the proposed system intends to postpone the permanent abandonment of wells, postponing their high cost by using less complex logistics and process than the traditional methods used by the industry. Thank you very much for your attention. I hope the information I gave you today was useful for you.
Thank you so much, Pedro, for your presentation. So I have a couple of questions here, so we still have some time to answer. So the first one is a really basic one. So you are presenting a solution that can not replace, but is an alternative to have a permanent abandonment of wells. But we know that some wells in Brazil, or mainly Petrobras, are old-fashioned wells, and they have different types of Christmas trees. So this system is compatible with these different types of Christmas trees. And as you said, sometimes you have problems of maintenance of these equipment. How is it? Can you elaborate a little bit?
Yes, it's because, as I said, we are focusing on just one type of Christmas tree. And here in Brazil, because our invention is purely applied here, we studied the market here, and there are a lot of Christmas trees that have that characteristic. That said, that it's Christmas tree with vertical connection model.
Okay. So in terms of powering, so when it's not connected to the ROV, how the system works? Only the gauge works? How is the monitoring
this,
without the ROV?
yes, in this form of operation presented, the system is always powered by the ROV. When ROV is not operating the system, it is in passive form. That is, the safety valves of the register modules are closed for safety, but no monitoring is being done. Thus, we have already the AMP regulation as the required monitoring is periodic. Even so, the proposed system is already patented by Ouro Negro, and it provides for more elaborate modification of the system, in which you could leave a battery embedded in the system that powers both the pressure sensors and a memory that records the state of the well when you don't have the ROV operating it.
So just an example, if you're having a leak or if you have a barrier failure inside your Christmas tree or inside the well, the system cannot reading this without the ROV. Just when the ROV arrives, that you see.
Yes, as we presented here, but as I said, this is the basic configuration of our system. In the patent, we have a more elaborated model, however, the patent includes a version in which the pressure sensors are constantly powered. If they register an anomaly in the well, an emergency system is activated. It releases a flag to the surface that signals that a particular well is presenting an environmental risk.
Okay, yeah, my question was regarding that. So if you have an fluid expansion or a different reservoir behavior that can create some leaks in there. And the last question that I have here is, since you are proposing a postponement in the abandonment, so this solution can be feasible for how many years? So how many years can you postpone your abandonment with this solution?
There's no time in the regulation, but our system is made to work for about 10 years. So it's the first estimative of how much time would you postpone the permanent abandonment.
Okay. So let's just wait a little bit if some questions arrive from our system. Okay. So Pedro, we will close the speech. Thank you so much for your presentation. It's a really pleasure to have you here. And if more questions arrive, we can address you by email.
Thank you very much, Igor.
Thank you so much. So for the attendees, it's time for a really quick break, so you can take some water or coffee and stretch a little bit your legs, and we will come back in more or less 5 minutes. So thank you so much, and don't forget to make questions in the icon in the top right of your screen. So good afternoon, Ramon. How are you doing?
Yeah, good.
Everything good?
Good.
Thank you. So we are back for our session with our last guest, Mr. Ramon Ferreira. Sir Ramon Ferreira has Master in Mechanical Engineering, graduated from Cefet University in Brazil, with more than 10 years of experience in R&D and innovation projects applied to solutions for inspection and structural integrity of equipment and materials. With experience in consulting using advanced inspection techniques, advanced features in numerical simulations in welding demand, inspection and structural integrity. Qualified inspector in phased array and TFOT ultrasound techniques and other non-destructive magnetic and visual techniques. In addition, Ramon is currently a PhD student of Mechanical Engineering and Materials Technology with direct participation in the management and execution of non-destructive inspection projects in annular flexible risers in pre-salt Brazil. So let's give a warm welcome for our last speaker, Sir Ramon Ferreira. Thank you so much, and the floor is yours.
Okay, I will present here. Thank you for this opportunity. Our presentation is focused in an ROV solution for inspection using NDT technologies. We are developing and for a specific case, specifically problems that occurs at flexible risers. One of problem we have detected, it's annular flooding. The problems it's common to see in the field, and then using our knowledge to improve, regrouping two technologies using ROV and NDT advanced technologies, we developed a new kind of inspection tool. Yeah, I will start the presentation. So risers, flexible risers, consist in a subsea pipeline, yeah, and then here we have different layers of different materials, and then these different materials act together in a unique flexibility, and then we have results of a rigid steel pipe, yeah. But equal the steel pipes, we have problems, failures that happens in these components, and then we need to improve and adapt some kinds of integrity evaluation, specifically integrity evaluation. But for these complex materials, we need to execute some kind of research and development projects, and to qualify specifically procedure to inspect this kind of material. Okay, so it's a kind of information, good information for now. We can see in this graphic that it's 10 years ago, the most common failure in the worldwide occurs in external sheath damage. This external sheath damage is the most common problems, and then this contribute for many kinds of problems associated for the annular flooding. Okay, and then this problem occurs some other situation in a wire, the tensor armor wire, and then we have here an image to show you a good high flexible riser, and the external sheath damage, and then results in annulus flooding. The water inside these layers results in stress corrosion cracking, yeah, and then this in a few time we will have some tensor arm wire with damage and cracks. Okay, And then we need to improve our technology to detect the annulus. First, we have some kind of problems like the stress corrosion cracking, okay? So the project has some kind of steps, and these steps we have here. The first one, we need to understand the hyzer engineering data. Yeah, we need to understand more about these layers of material, and then with this information we improve some kinds of 3D numerical ultrasonic and stress simulation. We're using two softwares that's common to use in inspection and stress analysis, like SIVA and ANSYS. I will show you some images. And then in this project we could develop a new kind of probes, and then we need to research and customize this one and fabricate to use in this specifically tool for subsea. And then imagine it's not common to use a simple probe for like this condition with high pressure in subsea. We need to improve to fabricate a specific one. And then during this project we executed some laboratory tests and hyperbaric tests. I will show you some images, but in these conditions we could use a real samples of risers to analyze and to understand more the phenomenon of annular flooding. Yeah, and then we improved the design, the project design of ROV-scan. This is the commercial name of our tool. Yeah, and then we expect in the final of this year, yeah, execute a field test qualification for this equipment. Okay, so the next template here we have some images to show you. The first step, we started to simulate some conditions with this information about the layers and the materials used in a flexible riser. Yeah, and then here we have some cases that we need to understand how these layers work in a high pressure. So here I have images showing you that we need some deformation of these layers, and then this deformation causes problems in the science of ultrasound, and then we have new values of the time propagation, and then we could improve more analysis of this one. Each sample of riser needs to be analyzed in real condition in the lab or simulation with the informations. Okay, so this is some evidences of our improve. Here we have the laboratory tests. So we have some samples used in these tests. In this case, we executed some atmospheric pressure tests. We just put this kind of samples in a water tank, and then to force the flooding in the sample. Yeah, and then we designed some tools to improve the research. And then here we have some images to show you about our results, good results of detectability. And here we have a pair of samples: the dry condition without water, and then the flooded one to collect this signal. The differences of the signal. Yeah. Here we have a test demonstration video to show you how this works. This is one of our tool that we use for onshore inspection. Sometimes we have some risers that need to be repaired on onshore condition in the fabric, and then here we can detect the conditions of flooding of these risers after they then come for the fabric for repair. Yeah, here we have some data and the collection of data of all the perimeter, rotating the machine, the tool, and collecting all the data to analysis. Yeah. So the laboratory hyperbaric tests was an important option and important research step, because here we could put some samples in a high pressure condition, and then we could see some kinds of problems and some kinds of phenomena that only occurs in high pressure. And then here we could collect some data of each pressure. We could collected some variability, and then this data was used for our software of post-processing analysis. Yeah. So talking about the research, and then we talk about the research, and now we are talking about the project. And then all these research improvement we use it to design a new kind of tool. This is our new tool for inspection in a high deep condition. This is a new one, innovative, and this tool could inspection in multi-diameter risers. And for now, for example, we inspected some tips of riser with double external sheath. We inspected the tips of riser like gas injection risers and production risers with a small diameter and high diameter, like 420 millimeters of diameter. And then this machine, this kind of new tool, we could inspection turning around the pipe, and then we could inspectioning longitudinal inspection too. And then with these degrees of probe rotation, we could collect all the data of all the perimeter, and then this data was analyzed in an online condition. Yeah. And then all this data was performed to use in the analysis of quality, and another form is the quantity. I will show you something. Here we have the image of the real proportion of the tool. Here we have a ROV. The two are connected by umbilical cables to ROV, and then we have in the ROV, inside the ROV, we have some vases. We have all the information there with equipments, and then the ROV connected with the tool. We could inspection in the real time, and in this condition we could go for 300 bars of deep operation. And then here we have in some situations we could inspection in a vertical line or horizontal lines, because if we have the flow line rises, we could connect the tool and turn with another option and turn to see the other perimeter. Yeah. So we expect to expected to go to the field in October of this year. We had some stopped operations because we had the problems of coronavirus, but we still working in our homes and lab with all the security, and then these equipment are in development, in fabrication, and all the methodology and the tests were tested in the real conditions, real samples, and we have now some algorithm to use in our post-processing software. It's a kind of innovative software tool to use with this kind of new tool that we have. Yeah, and then here this development of ROV inspection are being used in a few times for high deep inspection, and we could use this for commission conditions. Yeah, and then here we have some data that we could use for this inspection, and then after this time we expect to have a inspection tool that have some applications in the field, but we can use this tool to inspection in onshore condition too. So if you know some cases that we need to analyze this kind of tool, we can use them for gas injection hyzer and production hyzers. This is the types of hyzers that we already executed the tests. Okay, so this is the final of the presentation. Thank you for your attention. I would like to pass question and answers.
Thank you so much, Ramon. It's really good to see this kind of tools and innovative solutions that in the future will be applied in the field. So I have a lot of questions here. I'll try to select some to pass to you to answer. And the other ones that I cannot pass because of the time limit, I will pass you by email. Okay? And then you can answer. So the first question that I have here is that you almost already answered. That you believe that inspection tool still in development could identify anomalous conditions for production lines? If no, please could you clarify the gaps of the technology?
Yeah, here in these conditions that we have the high deep pressures, we need to improve our algorithm to detect and to select the best signals to analyze. Yeah, and then all the problems that we had during this research, we could use many kinds of our skills, like using simulation, using the tests to analyze this phenomenon. It's not easy, it's a complex one, and then we need to regroup some kinds of technology innovation, like to design a specific probe, to design a specifically methodology to analyze the signals, to design a specifically tool to make the scanning of a specifically types of hyzer. And then this is the most steps that we need to pay attention for the research in this innovation project. Yeah.
Okay. And the ROV scan is only feasible for flexible lines, or it's usable as well for rigid lines?
Yeah, this tool was developed developed specifically for the flexible risers. But the project have a flexible condition to use a rigid one for riser using steel pipes. Yeah, we can use this one. We just need to develop a procedure specifically for this one to collect the data and to analyze this form of signal. Yeah, if it's possible.
Okay. So another question that I have here is that a critical part of the riser is the inner part of the flexible line connector. Could you please elaborate how to inspect that area?
The inner part, yeah?
Yeah, inside the flexible line connector.
Okay. We have some samples that we are using for our research, and then we have the specifically point to see we are expecting the focusing to see the signals of the steel layer, yeah, the potential wire layer, and then for our research we are expecting to make some inspection near the buoyancy of the risers, the places near the buoyancy, yeah. But for this case, we are using the ultrasonic technology to see this one, and the parameters used for this technique combined for the customized solution are giving us good results of the inner part of the riser, yeah. And then we are collecting this data and using specifically algorithm to regroup this all data of all the transistors used and to make some mid average data and to use some quantitative analysis and quality analysis. Yeah.
Okay. So I left the hot topics to the end. Now I'll talk about a little bit of stress corrosion cracking, CO2. So in flexible lines, do you see that this ultrasonic test is possible? So is a possible solution to identify this crack? Based on your experience, what's the minimum crack size that is critical for crack propagation? And if you see any other technique that can make this kind of measurement of crack instead of ultrasonic.
Yeah. First, we need to understand the phenomenon, and then when we could see interpret the condition of flooding riser, yeah, we interpret that the water started a progressing problem of stress corrosion cracking. But when we use this technology to analyze with ultrasound, we are focusing in steel wires, yeah, and then we can detect some cases, the broken conditions, the failures of each wire. When we turn the machine, the tool, yeah, making the scanning of all the perimeter. But we are developing a new kind of methodology to analyze small cracks, yeah, using another kind of configuration of the parameters. But we expect to see some kinds of problems like 1 and 2 millimeters of cracks. We are developing this methodology. We expect we are having some good results.
And do you see any other technique that can predict this kind of cracking?
Yeah. We are working too in another techniques, NDT techniques, specifically for advanced ones. Another option is to use magnetic techniques combined with ultrasonic techniques.
Okay. So Ramon, I have some sensitive questions here. It came by the audience, so but if you are free to answer or not. So the first one is if you could elaborate, since it's on development tool, if you could elaborate in the daily rate cost expected for the ROV scan tool.
Okay. Okay. Sorry. The sound is not good.
Oh, sorry. Yeah, if you could elaborate regarding the daily rate costs for the ROV scan. I know it's a sensitive question, and you feel free to answer or not.
This specifically condition it's specifically for the project, yeah. And then I prefer don't answer this one, but we are working for to have a tool, ROV tool, competitive with the market, yeah. And then using innovative and good technologies to work in these high pressure conditions, extremely conditions, and then we are using a kind of balance to have a good results in these two to make some competitively market condition, yeah, with another partners, yeah.
And the last one here is if you have any like specific agreement with operator, or if you are available in the market to support other IOCs, other companies.
Yeah. First, we are thinking to work in that we are the operator, yeah. And then I think it's possible to have some partners for example, to sell this equipment. But first we have a team to work with this to solve all these conditions in the field of operations, and then we have an equipe to work in inspection in the field and to make the consultants of all the signals and to make this online data analysis, yeah, with these guys.
Okay, so the organization committee just told me that we have time for one more question, and the question here is if you could inform the frequency considered for your lab test in the ultrasonic test.
The frequency used?
Yeah, that you consider for your.
Yeah, it's a sigillous information of the company, yeah, but we have more than one frequency used, yeah.
Okay. Okay, perfect. So thank you, Ramon. As I told you, the questions keep falling for me, and I'll just send you by email the other one.
Okay.
Thank you so much for your availability and your clearance.
Okay. Thank you very much.
Thank you so much.
So we have finished the last day of presentations into the room number 2 of the 7th Galp Open Days. We would like to thank you all for attending the event and for the very interesting presentation. You can continue in room number 1 for the closing session with Galp CEO Carlos Gomes da Silva. Thank you.
Thank you, Natalia. Thank you, Ramon, once again. Bye-bye.